You guys able to see my screen? Okay, great. All right. All right. So, with this session, there are a few things on top of my mind, and then I'll discuss them one by one. But feel free to interrupt me and ask me any questions that's probably you had some doubts, and we can clear on the fly. We'll talk about the building blocks of the large scalable system, what it means to be a large scale system, and we'll talk about the scalability, what are the components and scalability, and we can talk about some of the Azure offerings to build a massive or a hugely scalable system. And I was thinking about a checklist to build scalable system, which is something that's given me. I was not able to complete that, but I can give you the references where you can find that checklist to if you want to start building a scalable system, right? All right. So when we talk about any software system, you can broadly categorize them into two parts. Two things. One is the compute-intensive services or the systems, or second is the data-intensive systems, right? So so when we talk about a scalable system, around like 70 to 80% of the system now are data-intensive, you can say. The numbers may vary, but you're likely to get working with more data-intensive application. So the majority of our discussion will go towards building a scalable data-intensive application, right? So now we'll talk about what is scalability, what are the components. But before that, we'll step back and then see what are the building blocks of a large-scale system, right? So when we talk about large-scale systems, apart from the functional concerns, we talk about many non-functional or cross-country concerns, right? One being the scalability, availability, security, resiliency, observability, reliability, performance, and many more, right? So primarily this session is focused and geared towards scalability. But let me assure that we will discuss a bit about other things. So can anybody just tell me what's your understanding on scalability? What do you mean by that? Anyone, please?
It's about handling large amount of data without the system breaking.
Mm-hmm. Okay. Anybody else? Anybody else has a different opinion about that?
It's about like the capacity of the system. Suppose like if the number of users are increasing, then what will the system do? Suppose like in a large scale system, if the number of users increases, the system will scale up. Like it will identify patterns and stuff like that.
Okay. Okay. Good one.
And it can.
All right. Okay. We'll come back to scalability, but let's talk about other stuff. So quickly, availability. What is availability?
Like your service should actually be available. Suppose like I'm opening my Outlook and I'm trying to send a mail to someone else. So at least the mail should go. So the server should be at least available.
Okay, so we tell that is the percentage of uptime, right? That the percentage of uptime the service is available, we call it as availability, right? Right. So and the contrast we call it as if it is the service is not available, we call it as a downtime. So that's it for availability. Security, we know, it has many spectrums and aspects. Resiliency. Anything? Any opinion about resiliency? Any idea about resiliency? All right. So resilience is something you can talk. You can tell that the fault tolerance of a system. If something goes wrong, how the system is able to get up and running, how quickly it's get up running, and what are the measures it's taking. It's called a resiliency, right? So let's say my service may have a dependency on other services, 10 services. If some of the services go down, so does it make sense for me to go down, or do I have any fallback mechanism? That's called resiliency, right? Now let's talk about observability. Any idea about observability? Is it a very new term for you, or have you heard about this one? This looks like a very new term. of course.
Yeah, this is email from.
All right. So observability. When we talk about observability, what we tell is that what are the logging and monitoring aspects of a system. For example, if you are building a large-scale system with 100 number of components and pieces, you must ensure that every operations, every dependent operations, every your network infrastructure and your how much CPU is being consumed, how much memory is being consumed, how your node is performing. Everything has to be logged so that you can troubleshoot any. Let's say if something goes wrong, then you will be able to pick those information and able to process them and troubleshoot that. Right? Without that, you cannot build a large-scale system. I mean, it's pointless. You need to have those kind of information on hand in real time, so that any point of time since something goes wrong, you should be able to process or massage this information and able to take action, so that you can have corrective measures, right? And reliability. Any point on that? And reliability.
Reliability is that like our service should be reliable enough for the external users or something. Like whenever someone requests data or something, our system should not fail in that case.
Okay. All right. That's one aspect. Definitely one aspect of reliability, and you are correct. So reliability is something that, yeah, go ahead, please.
Okay, you can just go ahead.
All right. So reliability is something you can see that if I'm asking a service whether it's able to provide me the correct information or not, right? That means it's somehow related to availability. It looks like, right? If the service is not available, it cannot be reliable, isn't it? That means, so for example, you think about a situation. So one is the correctness of a system, how functional the system is correct and able to serve you as per your need. Second thing is that the availability also reflects on reliability. For example, if for example we both are sitting working on a project, let's say you are doing that, right? If I go to you sometime and if I don't find on your desk, I can say that you are not available, right? That's your availability. But if I go you 5 times and you are still not available, probably I won't be able to rely on you. So you can think this as a trade-off between weather and climate, right? So reliability has 2 aspects. All right. Then performance. You know everything about performance, right? Basically, we measure through the latency and throughput. So the performance of any service or any application is measured by 2 factors. One is throughput and the latency, right? So do you know the difference between latency and throughput? Anybody can give a pointer? All right. Latency is something you can think of. I can give a very basic example. Let's say we both are playing. Let's say we both are playing. I'm trying to throw a ball to you, and let's say we are 5 meters apart, right? So if I throw a ball to you, and it takes, let's say, 5 milliseconds to reach to you, so that's the latency, right? So I throw you a ball. It takes 5 seconds, and you can throw me back. Probably it takes another 5 seconds. So 10 seconds is a round trip latency, you can say, right? But throughput is, let's say I am having 10 balls on my hand, and I am trying to throw one by one, right, in quick succession. So you might be able to pick it up, let's say 5 out of 10, or maybe 6 out of 10, depending on how quickly you are able to catch, and that's called throughput. So its throughput is always measured in RPS, so the request per second, right? Then we'll come back to scalability, right, which we are going to discuss today. So how scalability, and then we'll talk about the traditional way of how we have been developing services, and how we are able to people were able to handle the scale or the and say the number of large inputs or the number of loads that's usually gradually increasing, right? So initially when people used to start any system, as you see, they'll put a database, they'll put some maybe web application or maybe API, depending on what's the need, and client used to access those endpoints, be it a UI application or maybe API endpoint, and the application used to hit the database and at the data storage and get the response back to the client. So it was very simple, right? It was very simple setup, and everything started probably when we go get back. Probably everything started like this, and gradually the user load increased, right? So what people did is that they increased the size of their system. When I say size, it means they added more RAM, or they maybe added more CPU, or maybe they increase the size of their hardwares. But it has its own limitation, right? So, but we still call it as scaling, right? We call it as scale up, not scale out. So we'll come to that, but we'll call it a scale up. So so initially we try to handle that through adding more hardwares, more processors, so that we will be able to accommodate the increasing load. But it has its own limitations, as you know, right? Then probably people started thinking, okay, what are the other options available? And few smart people invented something called caching, and so they put together caching somewhere in between the database and the application, and so that the content can be preloaded into the cache or maybe on demand, and the user when access the data, it rather tries to read from the cache instead of going to the database, right? So it saves a lot of time. Of course, we'll talk about caching as well, but I'm just giving some pointers how things have evolved and how we are going to see some patterns around that. Now, then the load eventually increased, and they're no longer able to handle that through a single server or single application. They're forced to, or maybe there is, created multiple web servers or the web applications or the API endpoints. Of course, that's pose a challenge that how do we, have the responses from the client routed to the different instances or the APIs. That's why this traffic manager or maybe load balancer comes into the picture. Now the question is that since we scale the middle layer or the APIs, can we also accommodate that through the single cache system? Probably no, because the load has already increased. Now that means we need more instances of the caching system, right? And then finally, if you see, we ended up with creating multiple instances of the application as well as the cache as well as the database, right? So people eventually ended up here. So that's how things have evolved so far. But nowadays, when we talk about any system application, the user base is already huge. So, and we learned from our past experiences and experiments that we cannot no longer follow the same traditional path. We cannot build a single system and keep adding more components, but rather we will plan for building hugely the large scalable systems. And we'll talk about those components, how the patterns have evolved out of this kind of evolution. So now everything we'll try to sum it up, right? When we talked about scalability, we saw that there is something called replication, right? So replication is the very essential and fundamental component of scalability. When did we do replication? Of course, when we talked about the middle tier, the web application, we say that there are multiple number of nodes available hosting the similar services, right? And it's actually, if you look at the caching layer or maybe database layer, we see the similar thing, right? The replication. Then we'll talk about partitioning, right? Or sharding, you can say, which is very essential part of scalability. Then, of course, caching is one. And of course, having different replicated components, we need load balancing. And the fourth, which is very important, we'll also talk about offline processing. So these are the four pillars of, you can say, scalable system. Right? And all right, so I'm going to talk a little bit different things right now. When everything started, so you can relate back to the original, the different stages of application evolution. So when everything started, right? So when people started building small scale applications, everything put together into one system, physical system, you can say, maybe. So that means the database, maybe the application and the cache, everything has been put into one physical system. They shared the same memory, right? Same physical device, you can say. That's what we call this shared memory architecture, right? So people, as I said, if the user load increases, that means you'll have to add more RAM or more CPU or more hardware, especially. Then things have evolved, and something that came up with shared disk architecture. That means now they move the database or the data storage part to a different physical store, you can say, and put together into different let's say devices or the physical devices, and the web application or the logic is separated from the data storage, right, which is called shared disk architecture. You see most of the OLTP transactions, OLFE systems basically uses this kind of architecture. And things evolve. If you look at the last slide, right, if you go here, you see here, right, the application uses a different caching system and it has its own database. That means everything has been separated by this time, right, which is called shared nothing architecture, and which actually the shared nothing architecture was the first step towards the microservices architecture, you can say. Right? So in the microservice architecture, we share nothing. I mean, we just it's recommended that you don't share anything. So you own your own API implementation, you own your separate data storage, you own your own caching, and everything will be stored, I mean, or put together into different systems so that you have exclusive access to it. And we'll see. All right. So we'll start about, now we're going to talk about the different pillars of the scalability. We'll start from replication and partition. We'll move towards caching. Then we'll go to load balancing and then offline processing. But and when we talk about replication and partitioning, since I initially mentioned that we are going to talk about data intensive application, right? So most of my examples will be applicable, most of the data storage that's available by now. So you can say by and large, whatever theories or the examples I'll give you, they'll be most likely to, I mean, be used anywhere. Some of this, most of this data store mechanism called MySQL, or you can say SQL Server, MongoDB, Kafka, RabbitMQ, or maybe Azure Storage, right? So they'll be by and large applicable, all of the data storage. All right. Now we'll talk about replication. Any idea about replication? Anybody can give a pointer? What is replication? Let's try to understand. Anyone, please? Okay, I'd rather ask you a different question, right? You might have heard about duplication, right? Can you guess what would be the difference between replication and duplication? We'll start from there. Although they might seemingly similar terminologies, but let's try to understand what is replication and what is duplication.
So in duplication, like in replication, why do you replicate is that, let's say that I'm hosting my website on a server and that server suddenly went down. So there needs to be some other, like there needs to be a backup kind of thing, right? Suppose if something goes down, you still need to serve your customers. So in order to do that, you might be keeping the same code you might be hosting the same code on a different server as well. So you have a different server. That is a replication kind of thing. Suppose let's say you have a database is getting too many loads and it went down for some reason. Okay. And what you'll do is you'll maintain another database, same data, you'll put it on some other host. It's kind of like that.
And what is replication? Okay, what is duplication?
Duplication is like you can put the same data in the same host as well, right? So I think that is the duplication.
Okay. It's not like that, but there is no, okay, let me tell you that there is no hard difference between replication and duplication, but they're just offline though. So the thin line is that when you say duplication, the data is actually, so in either case, actually, you'll have multiple copies of the same data, you can say. Since we are talking about data intensive application, let's talk about data only, right? So when it comes to duplicating or replicating an application logic, that's different thing. So it's much simpler than the data, in fact, because there are many concerns involved with data replication or duplication, you can say, right? So when we talk about data duplication or replication, when we talk about duplication, right? So duplication is something is that you are syncing the data in a particular point of time. For example, you can choose to let's say you have multiple copies of your data in 10 different nodes, you might want to sync all these nodes probably at 12 a.m. in the night, where you have very less load onto your system, and you can say, at this point of time, I'm safe to copy all my data to different nodes. That's called duplication. But replication, it's something, it actually watches for the incoming data as and when things are coming, right? And it try to make the copies of the data available in all our other nodes on the real time. I may be incorrect saying that it's real time, but it's near real time, you can say. So that's the difference. But this is just a soft difference. This is not a hard difference at all. Right? So that's something I wanted to clarify. All right. So replication, as you know, so that means when you use replication, you can have multiple copies of your data, right? So that's the primary purpose of having replication. So what it enables in turn is that it can reduce the latency, so that because you can have the copies closer to your client, right, or the user location, you can say, and also since you have multiple copies of your application or the data, so you increase availability, right? And since the data is actually available closer to your to user location, or maybe having multiple copies, you also increase the read throughput. Right? And we'll talk about initially. So I want you guys to understand what works, how it works behind the scene. Then we'll go about understanding what are the Azure options available to making things scalable, or the system scalable, and how they internally use this kind of mechanism, right? So we'll talk about some of the replication strategies. You might be aware of this one, but I'll just have a very quick 5 minutes of brief overview of the strategies for replication, right? So so any databases, the list of databases I showed you, most of them actually use any of these three strategies, and you should know that. So the first strategy is single leader, and the second was multi-leader, and then there is leaderless, right? So in a single leader system, usually you have, I said, like you have multiple copies of your data or your system, right? So one node will be called as the leader, or the primary or master. So you might be hearing many of the words, but they are used interchangeably. And then the rest of the nodes will be called as followers, or you can say replica or slave or secondary or standby, whatever you may be called, right? And once the data reaches to the leader, it replicates that data to the followers, you can say, right? And the client can read or write from the leader, but the clients can only read from the followers replica. This is one we call the single leader application, single leader replication, right? So, but it has one you can say advantage and disadvantage. But if you look at, by and large, the different relational database like MySQL, Oracle DataGet, and the NoSQL database MongoDB and RethinkDB, these are the systems they use single leader application, right? Single leader application has its own kind of disadvantage or the cons as well, where you can say, how do you set up a new follower if the follower gets what do you do if a follower has a failure, or maybe what do you do when a leader is failed. There are many other concerns, right? But apart from that, we should understand how this data change replication or the data stream management happens. So you can see that, as I shown you, so the data is replicated from the leader to the followers, right? So it could be done synchronously or asynchronously, right? And so we'll talk about synchronous replication. So with synchronous replication, as soon as the data reaches to the leader, it makes sure that the rest of the followers gets a copy of that data, right? So being it synchronous, the followers are guaranteed to have an up-to-date copy of the data. But this looks impractical, because let's say if one of the follower doesn't, let's say, reply back, because the synchronous communication has to wait for that, so the leader has to wait in turn, and there will be a lag to send the communication back to the user, right? But then it comes to the asynchronous replication, where the leader can continue processing the data even if some of the follower fails, because just asynchronous data replication of the communication. But the downside is that the data is not guaranteed to be durable if the leader fails. If the leader fails, that means by the time the data may not reach any of the follower, basically. That's why people come with a middle ground, which is called semi-synchronous replication, and where the leader choose one follower to be synchronously replicated, and the rest of the followers can be asynchronous. And this is extensively used at Facebook. In fact, many other systems also use. Just I gave a link there so that you can read how they are using this semi-synchronous replication. All right. Then coming to the multi-leader replication, this is popular when in multi-data center operations. Maybe your data is replicated over regions, and then you in that case you might have a leader assigned to a particular region, and as and when the data comes, it replicates all the new data onto their local region. And of course, there is a question that how does this data comes back to the other region, basically. So and we will end up with probably something called merge conflict. So anytime that a multi-leader replication is used, that means you would need a conflict resolution. For example, Google Docs, it's a multi-leader replication system. And there are some systems which are leaderless. They choose that we do not need to have any sort of leaders as such. And whenever any data comes, we'll just write to all of the replicas, but probably chances are that one replica may be down. In that case, the users get a response back from few replicas and may not get from the other replica, and this poses a problem. And then that is solved through something called versioning. We don't need to go through the details of this, dig into the details, but you should know that there are different strategies of replication, right? So most of the database actually use any of these three styles, you can say. So the example here is the Amazon DynamoDB, Cassandra, or Voldemort. These are used the leaderless replication. And partitioning, I don't need to tell about that. Partitioning is something that you should implement. Partitioning could be horizontal or maybe vertical, but most of the systems now, you would be more comfortable having a horizontally partitioned data, and which is popularly called sharding, right? So and you'll have to choose carefully the kind of the partition ID, because partition ID is something that you choose once, it will be difficult to change it. And there are many systems who has encountered failure because they later on they realize that the chosen key is not appropriate in long term, which creates a problem. And there are many databases now have supported multi-key partitioning, so you should be able to leverage that, right? And now, since we're talking about the storage systems, right? So Azure provides different types of storage options, including Azure SQL databases and the Azure Database MySQL. These are RDMA systems. Key value stores like Cosmos DB or Azure Redis Cache. Document-based systems called Cosmos DB, GraphDB. Object storage, which is known as blob storage, and file storage. It has its own Azure file storage, right, to store large file systems, right? All right. The reason I'm giving this data is that so that we can use later on for when we build a scalable system. And then we'll talk about caching. Caching is usually it's done in two ways. One is the private caching, and the second is shared caching. Private caching is something that any system that's that store their data locally in memory, can say, right? So if you are building an API, you might want to keep some of your data locally on your same box or the physical machine, you can say. So that becomes private to you. And when I say same box, I think it's the same in memory. So the in process data. And most of in distributed system, this in memory, the private caching may not be very helpful. So because the data is always distributed, you never know from where it which is the up-to-date data. So you always prefer to have a shared caching or distributed caching again. I'll talk about that. So Azure Redis Cache is very promising and dominant in Azure Cloud Platform, which is very so if you look at some of the data points here, right? So the Azure Redis Cache has a throughput of 180,000 requests per second when it's in P1. P1 as in is a premium tier, in fact. So all of these, if you know about the Azure or AWS, you talk about any cloud vendors, they provide you different tiers. That means if you opt for standard tiers, you have some limitations on the resources. If you go for premium, you pay more, but you also get more, right? For example, if you use the same Redis cache in C3 or maybe a standard version, you get a little less request per second, or RPS, you can say, right? And if you enable Redis clustering is again which is enables you for the distributed caching system. So the throughput increases linearly, where you can say, let's say you get like 4 million requests per second, right? So it's able to, if you have 10 number of sets, right? Then we will talk about Azure load balancing. The load balancing options, again, if you go about to my previous slides, so I talked about the use of load balancing, of course. But the load balancing, in fact, is not limited to only be used in the web application. Load balancer can be used almost in anywhere. Let's say if you have let's say cache, then you can also use internal load balance. You can, if you have multiple APIs, cluster API, you can have an internal load balancing, right? Of course, if the client is accessing the API from outside, they'll have to pass through external load balancers. So that's why there are many different options provided by Azure, right? So then a group called global, and then another group called local. So that means the global Azure load balancing options are available so that it can interfere with the outside user, right? And the local, or you can say the regional load balancing options provide you the internal load balancing. For example, Azure Front Door or the Traffic Manager are two examples of the global load balancing options, where it can, so whenever the user or the client try to hit the API, it actually be the API endpoint of your traffic manager or the traffic manager, not actually the API. Now the traffic manager will be configured so that it can redirect a particular, let's say, API endpoint to another internal API endpoint, right? And internally, you can also employ application gateway and Azure load balancer, so that you can create cluster of services, and then they can be load balanced among each other. On the right hand side, I gave you a pretty flow diagram where you can understand if given particular circumstances, how do you pick one load balancing, or how can I actually combine multiple load balancing to particularly solve your purpose. Any questions so far? Probably I might be talking too much, so probably I can take a pause and then see if you have any questions. All right. Okay. All right. We talked about offline processing is one building block or the pillar of scalable systems, right? When we talk about offline processing, there are many instances which you will encounter in the real time, in the real world, is that you may not want to build a service which will just read the data and send it back to the user, right? So for example, let's say you think about a situation of uploading a large file, maybe just not one user, maybe millions of users are uploading files. Think about Google Drive. Think about any such any sort of file storage systems where you are uploading files or saving files, you can say, right? And you do not need any response back immediately, right? What to do is that it will process the data offline. That means it will send the request to the server. Server takes the request and process, and as soon as they are done, they will send a response back to the client that we are done, right? So they'll give a 200 OK message. So in that case, you will get a huge number of requests to the client, from the client to the server. In that case, there is a very common approach at what we built it, Ajay. These requests do not need to be solved immediately. That means you can queue. You should have a mechanism to queue this request, and then some background logic or the background processor should take these messages either one by one or maybe in parallel. That's your strategy. Basically, you will have to build and do all the processing and send the request back to the client. and let's see what are the options available in Azure to do such kind of processing. One is the Azure Service Bus, the other is Event Grid and Event Bus. Azure Service Bus is something where you can say that it is, it takes the data in terms of messages. That means a message is something nothing but a command, right? So you can put any sort of arbitrary data. It doesn't have to be arbitrary in the sense your application should be able to understand that, but you can put any message or any data that could be readable to your worker, and those messages can be processed by the you can say your worker, and then they'll be able to process it. And in case of event grid, so there is a difference between the message and the event. Basically, message is something that probably you can see it as a command which encapsulate probably some instruction to say what to do next. But event is something that's generated, as in when some in the reaction to something that's happening in the real time. For example, there are so many IoT devices that's producing large number of data, right? So, or maybe the one event might be creating one more event. So those events are actually, if the IoT devices or any sort of events are generated in a huge chunk, event grid may be a better option. And event grid is actually used to process a discrete set of events, whereas event hub does the same thing, but it's only designed to have this have the streams of events to process, right? So that's the difference between these three messaging options. All right. Then finally, we talk about Azure compute options. So I talked about the different pillars of scalability, right? We talked about Azure, the offline processing. We talked about the load balancing, right? We talked about caching. Then we talked about the different kind of replication and the partitioning strategies, right? Then the final option, final thing that we should discuss is the Azure compute options. So when you talk about Azure, so there are a spectrum of compute options available. So one end, if you talk about the serverless computing, the other end there is a cluster of servers, right? So anybody knows about what is serverless computing, or maybe cluster of servers, and how do you distinguish between the two, and what comes in between, maybe? Anybody has heard about Service Fabric or maybe AKS? Kubernetes, anybody knows about it? All right. So, okay, I'll talk about serverless first, and then we'll talk about cluster of servers. And there are some compute options in between, like so like a PaaS service or maybe IaaS service. Serverless is very popular. It's you can so the example of serverless computing is functional service in Azure, right? So AWS has its own. I think AWS Lambda is one option. So in serverless, the user doesn't manage anything of any infrastructure or any platform specific. There's no platform specific need from the user. In fact, it just know that I have some logic. I want to deploy it somewhere, and I don't know where it goes. But it'll just run. The infrastructure will take care of that, how it's going to run. But it comes with its own disadvantages. That so if you are building serverless, any serverless application, it will be tied up to that particular cloud infrastructure. That means you cannot just take Azure function and run it on AWS Lambda, because the SDK integration is so tight that it only runs on particular cloud. Even if you talk about AWS Lambda, you cannot just bring it to the Azure cloud as right? As is, you'll have to make changes to the initial SDK plumbing code and everything, and then make sure that it runs on a different cloud platform. That means it's not actually platform agnostic. So that's but rest assured, it actually it gives a very highly scalable system where you do not need to worry about where the code lies, how it runs. It just makes sure that whenever there is an event occurs, that the new instance of the application will be triggered, and it will automatically run your application code, basically, right? Then in between, when we talk about cluster of servers, we'll talk about two major offerings. One is the Service Fabric, other is AKS, right? So Service Fabric is something that's very fundamental to the Azure itself, Azure cloud itself. So most of the services of Azure, for example, Azure SQL database or maybe Azure messaging, there are many services which run on top of Service Fabric. That means the Azure cloud team itself rely on Service Fabric. So it used to build, to host microservices in millions of microservices, and it will be able to handle that load. And there is one computing, the computing option that's available recently is the AKS. You know about Kubernetes. The containers are actually taking a buzz in the market. All right. So AKS is nothing but the orchestration platform for the containers. So containers are nothing. You can think of a probably abstract package which contains your code as well as your configuration and all the dependencies, so that you do not need to worry about or saying that, hey, this code works on my machine, but this code doesn't work in other machine. So this is more than the case when you are using containers, right? So because it contains everything for you: the code, the logic, the configuration, the dependencies. Now you should be able to run that in any platform as such. So for example, you can build. You can use .NET Core or maybe you can say any JS-based application, and then able to run that in Linux as well as being that the Windows systems, and it will be able to run seamlessly. Now the question is that if you are running hundreds or thousand number of containers, there should be some orchestration platform. When we say orchestration platform, it means that if a container goes down, who is going there to bring it up? Or maybe how do the two containers communicate between each other? When I say container, it's nothing but, again, it's just a package that actually holds your logic and code, right? So there has to be somebody who should take care of all these different concerns of containers or the runtime behavior of containers, and that's what we call it as, that's the name. The orchestration platform is Kubernetes, right? And then in between there are few offerings available, which is nothing but you can call it as IaaS or PaaS services. So if you talk about IaaS, it's majorly the virtual machines, and it's PaaS. I think you can name any cloud service or the Azure service. You can name it as a PaaS service, like API service or maybe app services, or maybe you can say Azure messaging services. Most of them, they fall into the category of PaaS services, right? And now the next question is that if you have so many Azure compute options available, how do I choose one? Just like we told that if you have number of messaging services available, how do you choose one? If we say there are many databases available, how do you choose one? Of course, there is a question if we have different Azure compute options, and how do we choose one in which circumstances, basically, right? All right. So if you look at this, again, give you a very baseline overview of what do we start if you are building a greenfield, if you're working on a greenfield application or maybe a brownfield application, or maybe if you are building a brand new, then do you require full control, or maybe it's a microservice architecture, or it's just an event-driven workload. Depending on that, this workflow can tell you like which Azure compute option you can use in case of which circumstances, basically, right? So that gives you a baseline. All right. Any questions so far? Any questions? Maybe if you have any questions about how the database systems works, maybe I can explain. If there is anything that you're not able to understand, I can explain somewhere in between. I can go back to the slides, or maybe or else we can continue. Did I lose you guys? Check. All right, looks like everything's good. All right, so we talked about largely the systems or the components of scalable systems. Let me go back. So we talked about replication and partitioning and how the different databases are using that. And we talked about caching. We talked about load balancing. We talked about offline processing. If you combine, so to be able to build any scalable system, you need these 4 components built into your services or the system, right? So without one of them, probably it will not be highly scalable system. So you'll have to make sure that your data is replicated and well partitioned. You'll have to make sure that the data is cached correctly, so that whenever the user needs or demands some data, it gets as quick as possible. And of course, caching has its own different strategies as such. The cache doesn't have to be residing in the server. The cache can go or come up to the client, right? Because it increases the data locality. And we talked about load balancing options, and also we talked about offline processing, right? So these are the 4 items. By and large, they make up the highly scalable systems. So that whenever you think about building a scalable system, you'll have to think about these 4 components. Right. The only thing that probably I was not able to share with you guys is a checklist of the things you should do when you are building a scalable system, but I'll make sure that I share the links with you. All right, so that hopefully this gives you a very high-level overview of the Azure and the different components of scalable systems. I know this is going to this has been a very 1,000-feet overview of the scalability part, but trust me, when we talk about a huge building a large-scale systems, it's going to be a discussion of like 30 days or a month's time, right? So probably if you are willing, then we can have more sessions on digging deep into the areas where things are gray. For example, load balancing or maybe caching strategies and all. But hopefully this gives you a very a brief overview, 1,000-feet overview of how we should build the scalable systems. Let me know if you have questions. All right, are you good then? All right, thank you guys. Right, thanks for that.